Righty, folks. And so our speaker today is Simon Sponberg from Georgia Tech. Simon got his degrees in physics and biology at Lewis and Clark College in Portland, Oregon, which means he's a terrorist. But
He'll take that for something.
then he got his PhD at UC Berkeley, which I guess means you're also an anarchist. Yes. And then went on and did postdoctoral work at the University of Washington. He's here because Paul Chaikin was always like, "Did you see a good talk?" And I was like, "No, I haven't seen a good talk." And I saw his talk at Market, and I'm like, "Oh, that's a good talk." So you are going to be entertained. This is a good talk. He's won numerous awards, including the Career Award, the Klingenstein-Simons Fellowship. He is the Glenn Robinson Professor in Complex Systems, which replaces a different named award you got the year before. So we are honored and graced, and you're going to enjoy this.
Well, thank you for the invitation to come speak to you. I really like giving this talk to a physics audience, and I think I sometimes call myself a re-reformed physicist because I started in physics, left physics for a little while, came back, and I think the challenge of putting up a picture like this is that it's very easy, I think, to be impressed and awed by some of the beauty and the complexity that you see in biological systems, but it's challenging sometimes to say things about those systems. And I think the key, of course, to talking about physics in complex systems, whether they're condensed matter or living matter, is the idea of emergence, right? By Anderson, he was talking mostly about condensed matter systems where, the behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood simply in terms of the extrapolation of the properties of a few particles, but instead at each level of complexity, entirely new properties appear. And I think when we talk about life and living systems, it's actually, I think, was made to a finer point by Schrödinger, actually. He wrote this little book called What is Life that I recommend to people. He said, from all that we've learned about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to the ordinary laws of physics, not on the ground that there's any new force, that's what he meant by the ordinary laws, right, or whatnot, directing the behavior of single atoms, but because the construction is different from anything we've yet tested in the physical laboratory. And I actually like to use the word composition instead of construction, because it's how things are put together. And we have good news for Schrödinger that we do bring these systems now into the physics laboratory, and we've been trying to study these things. But life is a very particular kind of emergence. It's a special kind of emergence. And it's because there's a singular process that's acting on life that's not acting on other kinds of complex systems. And that's the process of evolution. And I think what is so important about what evolution is doing to this composition is that it is driving functionality. And functionality doesn't necessarily mean optimality, especially for any particular singular performance. But we know that in the principal ideas of evolution, that the composition of these organisms, the ones that will survive, tend to be the ones that have functionality in their environment. And so it's actually remarkable to me that you can move around in the environment, or that animals can move around in their environment with this amazing collection of neurons, muscles, skeletal elements, complicated environments, and that anything works at all. Right? And I find that actually very inspiring, and I want to understand that. And I used to think that maybe the way to understand it was to understand everything from sort of breaking down each part of the system. But I think actually the key is in the composition of those systems and how they interact. And you can see this actually in some of our robots. We have pretty much robotic components that are better than, or at least as good as anything in biology, but it's still hard to put robots together to the level that work with the kinds of capabilities that you see in biological systems. And so people have done this for a while, right? I mean, and I think this kind of form, the place that I really like to look for functional emergence is in motion, and specifically locomotion, because it's a very easily accessible, understandable system that's extremely important biologically. It's a main determinant of performance for animals. All animals move. It's a defining feature of them. We can go back to Muybridge and Hildebrand, who were systematizing gaits and looking at kinematic patterns that emerged from that. That was maybe a little unfulfilling because we wanted the dynamics under that. In the 90s and 2000s, building on some early work in the 70s, there was a formalization of these gaits into dynamic principles or templates, the most famous of which is maybe the spring-loaded inverted pendulum, this idea that when you run, the way your center of mass moves is it rises through the air and falls falls like an upside down pendulum, and then your leg acts like a virtual spring, compressing and returning energy. And this ends up being a principle that can work for any alternating sets of legs, whether it's a cockroach, or I'm sorry, there's a cockroach in the top, a human or an elephant, alternating these sets of legs. And in fact, if you look at the effective leg elastic forces scaled to the to mg, to the weight of the body, that non-dimensionalized elasticity in the system is constant from cockroaches to elephants. So it's a common principle and a variant in the system. More recently, people have been looking a lot at what happens in highly viscous environments where Stokesian flow dominates, and so where you basically, once you stop producing forces, you immediately come to rest. And in these cases, what determines how you locomote through the environment is the configuration space, or the change in shapes that you go through. This was made famous originally by the Purcell swimmer, but has now been extended to think about movement from worms to snakes moving on sand, including by some of my colleagues at Georgia Tech. And it doesn't just have to be about the patterns of motion. When looking at locomotion, we can also find interesting interactions with the surrounding environment that can be really important. I think the most exciting of these is the discovery of the leading edge vortex, which occurs on wings of almost all biological flyers. Most biological flyers fly with a very steep angle of attack, such that you get flow separation. But because they're at a high, but not super high Reynolds number, the flow will wrap back around and form a bound vortex on the leading edge of the wing that actually assists in lift production. And this is true for insects, for birds, and even for maple seeds that are spinning down to the ground. And that was only identified really about 20 years ago. And we're still just trying to understand the physics of how this leading edge vortex is stabilized on the wing long enough to actually assist flight. That's a different talk. What my group does is we look at these compositional principles. So I'm very interested in trying to understand the physics of living systems at the physiological and organismal scale. The organismal scale is a really important level because it's at the level of the individual the selection tends to act. And sometimes you can have selection at other scales, but it's very dominant at the level of the individual. It's where life and death occurs, right? And so what I'm curious about is how the nervous system, the muscle physiology and its rheology, and the dynamics of an animal's biomechanics interacting with its environment produce this locomotion. And I describe my lab as working at the in-between spaces in these, looking at the compositional principles, trying to understand how the dynamics of one shapes the dynamics of another, and how when you put them together, you get something that can be seemingly emergently simple. You can oftentimes describe many aspects of locomotion with simple, meaning low-dimensional, oftentimes linear dynamical systems descriptions, and yet underlying that is a great deal of heterogeneous complexity. So how does this complexity collapse? What of that complexity matters? And are there common principles of how this is done that we can use to try and understand the diversity in forms and function of biological systems? And this is what actually inspires me as a physicist. So what I want to talk to you today about is a very particular kind of locomotion that I think is particularly interesting to study in this case because it's so challenging. And that's flight. Flight's evolved 4 times in animals, in the bats, the pterosaurs, which are now extinct, birds, and insects. And insects are probably the most successful biological group of flyers. They've diversified, it's been around longest in them, they evolved at first, diversified the most in there. If we just look at the family tree of insects, this is just at a very coarse level, such that if we zoom in at one little group here, the moths and butterflies, the lepidopterans, and here there's over 160,000 species with different forms, right? And if I just look at this one little group of what are called the bombocoid moths, these are the big hawk moths and silk moths. You may have seen these guys hovering around looking like hummingbirds feeding from flowers like this. They're capable of this really amazing feat of hovering in midair, casting back and forth up to 20 times a second to track flowers blowing in the wind. It's very easy for me to tell you impressive biological details about any of these systems.
Once one of these species gains flight and then it diversifies, do you ever get a situation where one then loses the ability to flight in order to, optimize for some other trait, or does that never happen?
Yes, and a good example of that is ants. Right? So then there actually are some flying ants, right? But many ants have lost that capability, and it's part probably because of the sociality. Although bees, which are very closely related to ants, still maintain that. So I think I'm going to talk about a slightly different transition in a minute between the 2 dominant modes of flight. There's actually 2 very distinct strategies. So I'll talk about the transitions between that. I don't have a lot to say in this talk about that. switching back and forth, because I think there's a lot of things that can cause that change, that can sort of drive that biologically. I think the physics question of how do you generate these rapid oscillations and maintain the power to fly is the one I want to focus on, but it certainly does happen again. And part of the reason why a flight actually might be lost sometimes is it's very costly. It's very hard to fly when you're a small scale thing. It's flapping its wings back and forth. And so if we think about what determines the wingbeat frequency of animals, one of the things that we notice about all of that complexity is that there's actually a lot of different fundamental frequencies that insects fly at, from 5 hertz in some of these large moths to some mosquitoes and midges that can flap their wings 1,000 times a second. And if you go to the textbooks and you say, okay, well, what determines wingbeat frequency, you'll be told that it's body mass, that as insects get smaller, they have to flap correspondingly faster, because the aerodynamic forces scale superlinearly with the size of the wing. So as you make the wing smaller, in order to get the same aerodynamic force, you need to flap faster. If you actually look at the data, it looks like this, and people will draw lines on that like this. And I'm glad people here are laughing. When I show this to other audiences, they're sometimes like, oh yeah, that's great. Right? And they're like, nice scaling ratios. Actually, I think that's a really important point here, right? Is we can fit these lines. And actually, if you go back in the literature, some people are like, oh, well, the frequency scales of body mass with the -1/3 exponent. Some are a quarter, some are 4/5. It very depends. And you can see it actually, depending on what group of organisms, these are the different groups of insects. Like if I just fit a line here, or to the purple, or to the light blue, I'm going to get a different slope on each one of those, right? And so there's definitely a relationship between the two. And the general statement of, okay, as the animal gets slower, they do seem to flap faster, that seems to hold, right? But that's not this is not what's determining that. And I can make that point very clear by showing you these two guys. That's a bumblebee, and that's a bumblebee mimicking moth. And those pictures are to scale. They're the same body mass, and this guy flaps at 60 hertz, that guy flaps at 160 hertz.
So I've heard this factoid that bumblebees shouldn't be able to fly because they're too big, and I've never known what to make of this. And you seem like the sort of person that could.
We could go on. You want me to just drop this talk and we can talk about that? We could. There's 2 parts to that story. One is the unfavorability of getting smaller, actually, and the fact that you can hit power limits. And I'll actually talk about one of the reasons why they weren't thought to fly for a little bit in just a minute. That's because of the transition that you need to actually power flight at that scale. There is something really different about these 2 species. The main reason is that if you use classical aerodynamics of a fixed wing and you solve for Navier-Stokes around those wings, despite the fact that I'm going to do that in a minute, it tends to underestimate the aerodynamic forces, and you can't calculate that there's enough aerodynamic power from that. And that actually comes from part of that motivation for that leading edge vortex that I was talking about. It was the identification of those mechanisms that showed that the flapping wing of bumblebees and other insects could actually produce sufficient aerodynamic force to fly. So that's really those unsteady aerodynamic mechanisms underneath that.
As long as we're slowing down the talk, what if I add wing area? Like if I made a graph of frequency versus like wing area?
So wing area does scale roughly also with size. There is a relationship, but that one's even messier because you'll find really big exceptions. Generally, larger animals that are flapping more slowly, they'll tend to have larger wings because they can, because the big cost there is the inertial requirement to accelerate the wings back and forth because you're flapping. Right? But it depends a lot on wing stroke amplitude and things like that too. So there's a lot of factors that go in. So I'm not actually going to answer fully all what determines the wing frequency, because some of that is just dependent on life history and stuff, but I do want to talk about sort of the underlying physics that might be driving some of these patterns. Okay? So what I'm going to talk about today is this first idea of what really has been determining and driving wingbeat frequency and the wingbeat frequency that individual insects use. There's been a hypothesis around for about 50, 70 years now that insects fly at their resonant frequency, and I'll define what that means and what kind of resonance I'm talking about in just a minute. Then I'm going to talk about the fact that actually these 2 insects are flying fundamentally very differently. This one produces periodically forced oscillations, and this one actually has a mechanism inside its body that produces self-excitation vibrations in its muscles. And I'll talk about those 2 mechanisms and how both of them actually end up being super-resonant. And then we're going to couple those 2 mechanisms together and talk about how these systems can evolve back and forth from different kinds of flight strategies based off of transitions in the underlying physics of the resonant mechanics. Driving resonant. First, I want to acknowledge that this work that I'm talking about, especially today, is really the product of about a 10-year ongoing collaboration I have with Nick Gravish's group at UCSD. He's a really amazing biophysicist and an excellent engineer, unlike me, who's been doing a lot of the robophysical modeling for this. And we've had a lot of students contribute to different parts of this project over the time. So I really want to highlight these folks who have done this work over a while on this. Okay. So to tell you about why flight is challenging to start with, I want to turn to our robotics colleagues, because they've been trying to build insect-scale flapping robots for a while. And there's two big difficulties that they encounter. One is the problem of control, which is that hovering in midair is a dynamically unstable system. If you linearize the system around a hover equilibrium and you look at the eigenmodes of the system, there'll be a pitch instability up and down, and which is called the phugoid mode for anybody who's flown before. That's why you need to be careful about staring at the horizon if you're a pilot. And there's also a roll instability for flapping flight. And this is highlighted by this robot, which is actually a really impressive flapping robot. It's the first one that actually uses a biologically inspired, like artificial muscle to flap its wings, but it doesn't last for very long in the air. Okay, that's the problem of control. You have to be able to do control at pretty high, pretty quickly in order to be able to stabilize these systems. Half my lab sort of works on the neuroscience of those kinds of problems. That's not the main one I'm going to talk about, although it's going to come up again later. The problem I want to focus on today is the problem of power. And this is highlighted by this really impressive flapping robot. This is the first autonomous flapping robot, meaning that it doesn't have power wires going to it. And the way they power this flight is they put a little solar cell here that could collect light, and then they illuminated the room. And the secret that they're not showing you in this is that they had to illuminate the room to the equivalent of 4 solar suns worth of photons in order to power that robot. Okay? And it's not because those actuators are crappy actuators. The power density of the actuators that are used in these robotic systems is about an order of magnitude better than what the biological power density is. So it's something about the interaction, how you're channeling that power around and using that power in order to fly, that seems to be different from these guys in the insects. So the main idea, one of the main ideas that insects have been doing to mitigate that power problem is that they flap at resonance. And to understand that, you need to understand a really important thing about how the wings work. The muscles don't attach to the wings, at least not the main ones. Okay? They attach to the exoskeleton around the wings, such that this muscle originates here and ends here, and it deforms the exoskeleton like an elastic shell, indirectly driving the wings up and down through a propagation of strain through that elastic exoskeleton. And in a simple 1D model of this system, you can model it as the actuation force from the muscle being in parallel with a giant, stiff, parallel spring element. There can also be a small spring between the connection of the wings and the body. That ends up not being important, although we've tested it for a number of the different conclusions I'm going to say today. So for the rest of this talk, I'm going to ignore it, and we can talk about it afterwards if you want. That's then driving the wings up and down. You'll have aerodynamic forces, and then of course, because it's a flapping system, you need to accelerate and decelerate the wings on each half wing stroke. So this sets up resonant mechanics. You have a way of storing and returning potential energy, and you have kinetic energy in the wing. So this is not resonance. When I'm talking about resonance here, I want to clarify, I'm not talking about like flutter resonance of the wing going like this, the way that you would get like a flag fluttering in the wind. I'm talking about resonance with the elastic exoskeleton building up the large oscillations of the wings, okay? So, why resonance? Well, I think most in the physics community understand this pretty well, but just to clarify what I'm specifically talking about here and why it can help, is if you think about the muscle having a limited amount of power that it can output, where can that power go? Well, one of the places it can go is it can go into aerodynamic power, just pushing or doing work on the surrounding environment. Even though we model that as a dissipative force to the internal mechanics, that's actually your good power, right? That's what allows you to do work on your surrounding environment, get reaction forces, and move, right? So this is good. Basically, the moth wants as much of that muscle power to go into aerodynamic power to mitigate the power problem as it can handle. But it has another cost. It has to accelerate those wings back and forth. But it doesn't always have to pay this cost, right? If you have an elastic energy mechanism, you can mitigate the inertial power requirements of your system by every time you slow down your wings, you store energy against a spring in return, right? Pretty straightforward. So, and if that spring is tuned well to the system, then you can mitigate all of those inertial power costs and you can put all of your power in aerodynamics. But what do I mean when I say it has to be tuned to that system, right? Well, I always like to go to Calvin and Hobbes when I have a question. Calvin's demonstrating the importance of resonance and also the constraint on it, which many of you know, but I just want to remind you, which is that resonance works great, but only at specific frequencies, right? And so if you have gotten on a swing here, Calvin's not trying to store kinetic energy against an elastic potential energy, but against gravitational potential energy. You pump in a little bit of work on each cycle, and you build up a large amount of mechanical energy. And so the way I like to think about resonance is that when you're at a peak of a resonance curve, what happens is that your total mechanical energy in your system is high compared to the amount of mechanical work you can do per cycle. Right? That's a very important ratio to think about as we go forward. So when you swing, of course, it's helpful to swing at a specific frequency. And if you're like Calvin, and there's actually a frequency, the resonant frequency, that is kinematically optimal there. And if you're like Calvin, you don't go very far. If you wiggle at the wrong frequency, you don't build up those oscillations.
A question.
Yeah.
I'm used to think about biological matter as viscoelastic. And this thing, you claim that this is purely elastic. What is the material there?
Can you hold for 2 slides and I'll show you the material characterization and then I will tell you about the kind of dissipation. Is that okay? All right. So let's ask if that sort of description that I said is any good, and can we characterize where the moth is on this resonance curve? All right, so given the elements that I put up here, let's write out some equations to govern this, right? Let's abstract this out to think about a force acting against a linear spring, and so that spring is displacing. We have the angular motion of the wings, phi here, right? And then the last sort of component that I would need is I need something that converts the linear displacement of that spring and actuation to the angular motion of the wing. So I'll have a transmission ratio that has the units of radians over meters. And we've characterized that transmission ratio for a lot of insects, and it actually ends up being surprisingly linear and constant over the range that, of flights that we're looking at. There's a few insects where that's not true, but that's a different story. So what I could do then is I can write out these equations, and then I'll come back and try and validate these in a second. And I would have a driving force, or actually a torque, right? Because I'll put my transmission ratio on there. Then I'll have my inertial torques on the system, so that's just F equals ma, but rotational, right? And now I'll have my linear elastic term, again converted to a torque. And then I'll have my aerodynamic term in the middle. So let me unpack the aerodynamic term, which is a dissipative term here, right? So what is that big gamma there? That big gamma is a characterization of the wing stroke, and this is how we'll model the aerodynamic forces for the sake of this talk. This has been characterized for many years for insect flight. The point with gamma is that it's going to be a constant for any insect, right? It's a function of the air density, a non-dimensionalized drag coefficient that you can determine either geometrically or empirically by taking a scaled up wing. You can let it vary if you want. And then a series of factors that are just dependent on the shape and the size of the wing. The area, the radius of the second moment of area, the radius of the wing, and the length of the center of pressure. So these are all static measurements that are dependent on wing shape. You can have much more complicated aerodynamics, including those unsteady aerodynamic forces. Many of those are actually captured in this equation by doing an empirical coefficient of drag that actually does basically a quasi-static approximation of those unsteady mechanisms. It's far from perfect, but for this talk, what we're going to find is that even if we had greater aerodynamic forces that I'm not considering, this is going to be the conservative estimate for that. So let's start with these guys. And then all we would need to do to draw the resonance curve for a moth is we need to fill in these parameters. We can actually fit, if we get all the parameters on the right-hand side of the equation, we can fit Fm by what the amplitude of the wing stroke should be.
Sorry, you model the aerodynamic damping with a velocity squared. What is your choice?
Yeah, so this is basically you have the magnitude of the so the way that this equation is taken is you do what's called a blade element model. You cut each strip of the wing, and for each strip you look at its rotation, and then you calculate the translational velocity of that, and your aerodynamic forces is going to be proportional in magnitude to your velocity squared. We do it as phi dot times the absolute value of phi dot so that we keep the directionality correct, right? So that's proportional in magnitude to velocity squared, angular velocity squared in this case, but it still has that directionality. This is a really important equation. I only have like 2 equations that you really need to know. So if you have questions about this equation, this is it.
I guess one question is how accurate the velocity squared model really is. Because if you look at data, aerodynamic data, it doesn't work all that well over a broad range.
And it's interesting whether it works well or not. I think from again, it doesn't work well if you model each of the translational components separately from the rotational. We can put, so let me say, I can put the rotational angular aerodynamic forces in here. I can put the added mass forces in here. It doesn't change the story because what it's effectively going to do to my system is add additional dissipation to the resonant mechanical system. And I'll talk, when I bring up the FFTs in a minute, I'll talk about what happens when you do add that. And you'll see why it won't matter in just a minute. So for some insects, this is a good approximation. If you choose the right CD, it can be a better approximation. But yeah, there's a lot that goes on.
So, the surprising thing is that there is no linear term in phi dot.
There's no linear term in phi dot, right? There's no viscosity, right? Yeah, so why haven't I put viscosity in there? I was coming back to the question here. So this will tell you why, and I'm glad I put this slide in because it will show you. Basically, I have all these parameters from the literature. All I'm missing is K, right? And any other term that might be significant there. So let's characterize the material properties of that thorax and see what makes up with that. So my student took the exoskeleton of a moth, put it in a giant shaker apparatus. It actually has to be that big because this spring takes about 1 to 2 newtons of force to compress, despite it being about big. So it's a very stiff spring. He has to actuate it in the right action to deform the muscle and the exoskeleton in the right way. Here you can see this slowed down. So the head would be here, the abdomen would be up there. And here I'm deflecting that muscle like this. And you can actually watch these 3 dots. That's the stump of the wing hinge. And you can see that their motion is in this direction, even though the compression is in this direction. That's that transmission ratio at work, okay? So then we do this, and we do this at a bunch of different frequencies. And here's where the viscosity part comes in. When we look at the force displacement curve for that, what we find is something that has a little bit of nonlinear stiffness at the edges, and the other thing that we can do is put in a nonlinear stiffness here if we want. But notice here I have a bunch of ellipses that are going up in frequency, and they're basically lying on top of each other. That's not viscous dissipation, right? As I go wiggle faster and faster, I should get greater and greater dissipation. My ellipse should grow. This is structural damping. This is what you get from a dry friction model. And so actually your dissipation is proportional to your displacement, not to your velocity here. It's the model that they use for like construction of buildings and something. The other way of thinking about it is if you have an infinite series of viscoelastic dampers that are tuned to every different frequency in there and you sum them together. So there's a very small amount of velocity independent dissipation. We've run all these models that I'm going to show you with that term in as well as without it in. Again, all it's going to do is change my resonance peak back a little bit, and we're going to find that we're going to be above the resonance peak. So if anything, it's just going to increase our conclusions. But I can fit a spring to that term, and I can now put that in here, and now we have all of the terms to build that viscoelastic model, to build that aerodynamic damped model. So this is basically just a damped harmonic oscillator, rotational, right? But with a v-squared damping instead of a. And when we do that, we get a displacement curve, a resonance curve that looks like this, with a peak between about 15 to 17 hertz, depending on whether or not you include the stiffness that the muscle itself contributes. And if we look at where these guys are flapping, they flap out here at about 25 hertz. So they're flapping well above the resonance frequency. So there's a couple of things we should check here. First thing we did, we checked some different aerodynamic mechanisms. One of the things that we did, and if you want to see the data for this, I can show it afterwards. We made a model instead of with a fixed wing, instead of one that we could actively pitch back and forth, that would passively pitch up and down and incorporate those forces. And in that case, we actually get a very similar peak to this. It depends on what stiffness we use for the wing pitching, but it's always below this, again, because that tends to increase the dissipation in the system, and that's going to drive your this is your undamped peak, right? It'll drive your damped resonance peak even further to the left. Okay. So we're a little fortunate that it worked out that it was above resonance. It's harder to show that it's significantly below resonance. We should check some sensitivity. So we change all the parameters within sort of biological ranges, being very, lenient on what we consider feasible, and we can never get that peak to sort of move up to where this where the actual wing beat frequency is of the animal. So the animal seems to be significantly above resonance here. And then the other thing that you might want to say is, well, I have a damped resonant system. That doesn't mean that my only resonance is at my primary undamped natural frequency. I can have harmonics on top of that. And in fact, the harmonics will be set by the form of the function. This should actually give me the odd harmonics if you do the FFT. And then the amount of energy that I should have in those harmonics should be dependent on the aerodynamic term, on the dissipation that I'm having. But if we do that and we actually look at the time series at each of these points and we do the FFT, you can see it's a vanishingly small amount in the higher peaks, and they're not at the right frequency. And that's true if I simulate at the peak of the resonance curve or here. Okay, so the answer to Kelvin here is that the Hawk-Moth is neither Kelvin nor kinematically optimal, but somewhere in between. And it's actually operating right at about the point where it can get, it's doing approximately the same amount of mechanical work per cycle as mechanical energy that it has in its deformable thorax and the inertia of its wings. It's about 1 to 1. Okay, so why is it operating there? Well, again, we can turn to Kelvin. If you've ever been on a swing and you build up a swing oscillation, and I do this all the time because I have a 3-year-old, and whenever I take her to the playground, imagine you built up a large oscillation in the swing, and I said, on the next cycle, I want you to change your frequency by 50%, or I want you to change your amplitude by 30%. That's a difficult proposition, again, because your total mechanical energy is very high compared to the amount of work you can do in a cycle. Basically, the only way you can do that is somebody comes in and helps you slow down a lot and then pushes you again really quickly, right? So the cost of operating at your resonance peak is that it's hard to control your frequency. So we wondered if maybe the moths were operating above their resonance frequency to balance the needs for power with the needs for control. And so we wondered how much they were able to modulate that wing beat frequency from one cycle to the next cycle. And so we challenged a group of undergraduates led by Ryan here to do that. And they did the first thing that any good undergraduate would do when you challenge them with a problem like this. They went to Amazon and bought the first toy they could find, which happened to be a vortex gun. These things are great. They're like $10. They produce the most reliable vortex rings I've ever seen. And you can tune how far away they are, and you can shoot them off with the vortex ring and make it perturb. And then you can track the wings, and you can see how much the wing beat frequency is modulated from one step to the next. Okay. And we make sure the moth doesn't go splat. Okay. And what we find is that it's modulating its wing beat frequency by about plus or minus 20%. Around that resonance frequency from one wing stroke to the next. So it does seem to be using some of that. In contrast to the way that this Harvard RoboBee, sort of the best insect scale flapping robot, is tuned specifically to be at resonance. They even have the line in their paper that says, well, we tuned this to be at resonance to get the most power we could out of the system, but it made control really hard. We really wish we could make this a sub-resonant system so that we could take advantage of the control capabilities there. Well, the insects aren't sub-resonant, they're super-resonant, but they seem to be doing that balance.
Why are they super resonant and not so resonant?
Hang on, give me just a minute. Let's first ask how general this is. We first was like, okay, one hawk moth, let's look at some other ones. So we looked at a bunch of other hawk moths and their sister group, which are the giant silk moth, and we found here's both the undamped and the damped resonances, and they're significantly above the resonance frequency. The silk moths are above the resonance frequency, but so many of them are right on the line or very close to it, so they're flying very close to their resonance. Well, why might that be? Well, these hawk moths, we've actually, a previous postdoc of mine actually did the evolutionary biology of these guys and showed that these guys have wing shapes that are driving them towards lower efficiency, more maneuverable flight. They're more super resonant, and these are the guys that hover in midair and feed from those flowers. So they're really good at refueling on the wing. These guys seem to have much higher efficiency wing strokes. They're operating at resonance, and as adults, they don't have functional mouths. So they're on a fixed energy budget their entire adult lifespan. Again, I can tell you a million cool facts about biological systems, but the underlying key thing here is that they probably have a drive to be more efficient because they're on a fixed energy budget once they cut out of the caterpillar stage in emergence moths. And so they'll live 2 weeks, 3 weeks without ever getting any more fuel. Okay. So the story for the first part here is hawk moths do have resonant mechanics. They flap faster than resonance, giving up power for control. Before I answer the question of why super-resonance, we wanted to look, I've cheated a little bit, because if you go back and look in the literature, these are not the guys that were usually hypothesized to necessarily fly at resonance. And that's because it's actually quite easy for them to change their wing beat frequency, because their wing beat frequency is set by the nervous system, just like you set the frequency that you locomote at. every time the moth wants to flap its wings or you want to move your leg, what do? Your nervous system sends a pulse of activity to your muscle. It contracts and then it relaxes. It contracts and then it relaxes. In the muscles that control the wings of this moth, you get a pulse of activity called an action potential to the muscle each cycle, and that's in sync with the wing stroke. So each time the muscle contracts and relaxes. This is because this muscle is operating a lot like other muscles. So here's like human muscle as well. This animation is not biologically that great, but it gets the right details that we need here. When that action potential comes in, there are little bags of calcium inside each of these little repeating units inside your muscle called sarcomeres. And when that pulse comes in from the nervous system, it releases calcium, and that causes, from this thing called the sarcoplasmic reticulum, that calcium allows all the molecular motors inside of your muscle to start contracting, and you get a contraction. And then you relax by that calcium being sucked back off. So what sets the speed limit for these muscles, how fast they can contract and relax, is that the time scales of handling calcium in the system. And to make a long story short, basically the speed limit is about 100 hertz. Because of the kinetics that are involved in reuptake of calcium through these active transports, you can't contract and relax a muscle faster than about 100 hertz. But I told you that mosquitoes are flying at 1,000 hertz, and that bumblebee was flying at 160 hertz. So how are they doing that? How are they breaking this speed limit? Well, what they've done is they've decoupled their neural drive from their oscillations. So they're no longer forcing their wingbeat frequency at every individual swing stroke. Instead, they send one neural pulse and they get 8, 10, 12 wing strokes out of it. And the reason why is that they've decoupled force production from being dependent on the kinetics of calcium handling. So now, if you take a muscle out of one of these insects, like a bee, and you activate it, you get a constant force, and then if you yoink on it, you give it a little delta function in stretch velocity, what you'll see is that you'll be a bit of a rapid material response, and then it will actively produce force. The action of the myosin and actin molecular motors is actually induced by the mechanical stretch. That means the force is state dependent rather than driven by some periodic forcing function. So we call this delayed stretch activation. Delayed is a pretty bad word, but that's what it's called in literature. It's really sort of a phase-like, it's like a filtered version of it, okay? And so the secret here is then imagine if I have two of these stretch-activated muscles in antagonistic arrangement, so they pull on each other. I contract one, it pulls the other one. That one then automatically produces force, pulls back, and stretches the first one. And you set up a sympathetic vibration that can go much faster than the calcium handling kinetics inside a cell. And this is called asynchronous actuation, which is, again, not the most descriptive term. It's asynchronous because the neural drive is asynchronous with the wing stroke. So we'll use that term going forward, but it's really because the force production of the muscle is state dependent. Okay, so if I take this list of spectrum of frequency to body mass, and I draw a dividing line at about 80 hertz, and we look at which insects are asynchronous and which use this periodically driven harmonic oscillation, it roughly divides those lines, but everything above 100 hertz basically is obligately an asynchronous fly. And folks have suggested that asynchronous flyers are even more beholden to resonance. And I'll show you why. If we think about the force being produced by that stretch, we can model that delayed stretch activation as the sum of two exponentials. You can think of this with some rise time that's set by the ratio of these two time scales. So it really only has one time scale that's operative because these two are linked together. They always are correlated to one another. And so you can think of this response as being an impulse response to the system. If I give a delta function in phi dot, that's going to give a delta function of stretch on the muscle, and that's going to give me this response in the DSA force, in the delayed stretch activation force. If I have an impulse response, I can do a Laplace transform on that and turn it into an ODE that lets me predict what the force of the system should be as a function of the velocity. So now if I have a stretch on the system, right, that's going to produce a force. I can effectively take all the different frequencies of stretch that I could do and characterize how the force would respond to that trajectory of stretch. So the force here is not driven by like some sine omega t, it's driven by the velocity itself. So this is the second important equation. Because if I take this equation and I couple it to my spring wing dynamics, and I add in a little one parameter mu that scales the amount of force to match the wing beat amplitude, then what I get is a system of two coupled second order differential equations that don't have any driving force in it, but can set up true limit cycles or self-excited oscillations by the interplay of state and forcing. So asynchronous actuation is actually a fundamentally different kind of oscillation. It's a true limit cycle. It's something that's set up by the self-excitation of the dynamics of the system rather than periodic exogenous forcing. And that mu parameter just scales it. So, because this equation is coupled to that equation, people have said, this system must be operating at its resonance frequency, because now that oscillator is going to want to go at its natural frequency. But that's not quite right. There's another time scale that's at play. That's one time scale, the natural frequency of the system. But you've got this other time scale, which is the rise and fall time of the stretch response in the muscle. So how do those two interplay? So we wanted to ask if this kind of system is operating at their resonance peak. And so my student Ethan Wold, who just graduated about a month ago, and is now a Chicago fellow, he characterized all those same parameters for the bumblebee, and then in addition, he redid these delayed stretch activation experiments to characterize the parameters R3 and R4 in this equation. And then he was able to simulate the resonance curve for a bumblebee. And so here's the natural frequency, the kinematic optimum. Here's the damped the damped resonance frequency in gray, and here's where the bee is flapping at. So it's significantly above its resonance. And then he did that for a bunch of different insects. He wanted to plot what their wing beat frequency was relative to the resonance frequency. And so here's all those hawk moths and silk moths, the moths on there. Here's the bumblebee, and he was able to get data from the literature. The range here is sort of our range of estimates, or sort of best ability to bound where those values are. In the resonance frequency, we know what the wing beat frequency is for a honeybee and a carpenter bee. And then he did it for a bunch of different flies. Here's your Drosophila melanogaster is the filled in dot there. And so these guys are all at or above resonance. And then he was able to find a bunch of beetle data, that's the coleopterans, and even a dragonfly that he was able to put on this curve. And all of these insects are flapping at or above resonance. So again, why supra-resonant? So let's think about it for a second. What do you have to be in order to drive above or below resonance? Let's think about the resonance case first. Here's a plot of the torque as a function of wing angle for a system that's operating at resonance with a sort of perfect sinusoidal drive. And if we look at the elastic and the inertial torques, they're going to equal out, they're going to be equal and opposite of each other in a perfectly resonant system. They're going to exactly cancel out, such that the area under those curves, which represents the total amount of work each one is doing, is exactly equal over the course of the cycle. So that's the resonance curve. So this happens when that muscle times scale equals the resonant frequency, approximately. When it doesn't, now your torque is being produced with a different time scale than your resonance frequency, and a different frequency emerges from that interaction, from the combination of the two. And what happens is this ellipse tilts upwards. And if you look at what's happening in the super-resonant case, it means that your inertial forces are larger, your inertial torques are larger than your spring-driven elastic torques. And what this means is that the muscle has to help pull the wings. So it has to help, the muscle has to do a significant amount of negative work to help, and here you don't have a strong enough spring to store all of the energy that's in your moving wing. So the muscle has to help resist the motion of the wings. It has to actually pull back on the wings and give them a little bit of a braking force. Well, that's great.
So what
Muscles
is
are
the
good
broken line versus continuous?
That's one half of the cycle produced from one muscle, and then the torque produced from the other muscle. Because muscles can't produce negative torque, so you need one with the positive sign and one with the negative sign. It's just to show that there's two things. Big question.
And just to be clear, so the muscles are not acting directly on the wing, I thought, right? They're
Right,
acting
through that elastic transmission. Yep.
But you're saying even that is sort of a negative, it's a pull, in a sense.
So what I'm saying here is that if you imagine slowing down the wing, right, but you have an underpowered spring, you can't store all of that inertial energy, all that kinetic energy in the spring, right? So how do you get the wing to stop? Well, you have to have your muscles actively brake the system a little bit.
Yeah.
But that's okay because muscles can pull back on the system. They need to produce a force in this direction.
But they're breaking the exoskeleton, not the wing directly.
Yes, they're braking the wing via the exoskeletal transmission, but we model that all in sort of 1D case.
When the insect wants to stop flying, do this same muscle stops the wings from moving
They
altogether?
can, but we'll talk about that in just a minute. I want to talk about why not the sub-resonant case, because it's a very important thing about muscles. Muscles can only pull. And to do sub-resonant, if you only have two muscles that are antagonistic, if you have more muscles, you can do a lot of different things. But if you only have two giant muscles, and because of the power cost of flying, they basically maximized how much muscle space they can have for these muscles. In order to be sub-resonant, what you have is an overpowered spring. And now you would need your muscle to work against the spring instead of the inertia of the wing. And that would require the muscle to push. And muscles don't push, right? Muscle, my bicep can pull my arm in this direction. I can't push my arm in that direction. I need a tricep muscle to pull to do that. So because of the directionality and the asymmetry and force production in muscles, we think that in this arrangement, they're obligately at or above resonance. They can't be sub-resonant.
Why can't they just pull with the contralateral muscle?
The contralateral muscle has to do the positive work, so it can't do negative work in that part of the cycle. So it has to, the contralateral muscle is what's producing the torque to kick it around. So they have to, because your spring and your inertia aren't exactly matched, the two muscles for some part of the phase have to work against each other. In this part, the one working against the main active muscle during that part of the cycle pulls back a little bit. Here it would have to push back a little bit and it can't. So if you had a third muscle, you could do it. But there's not a large third muscle in here. All the control of the wings is thought to be done by these really little tiny muscles that do very fractional amounts of work that sort of act like the trim lines on a sailboat and twist and tilt the wings back and forth. So these are the main two muscles.
So out of, say, a million species, is there any that has a third muscle?
Yes, dragonflies actually do, but yet we still find them supra-resonant. And so I think that's really interesting. I'm not sure what's going on there. I'd love to study more of those. But very few other ones do because of this pressure to have as much muscle power packed into a limited space as you can. It makes a lot of sense to have just to maximize how much muscle you have for doing each of the two wing strokes. All right. Where are we at? All right. Good. I can finish up in just a few minutes. I want to tell this sort of last story because it sort of brings things together. So if there's these two types of actuation that are both super-resonant, how can you go back and forth between them? And this is an important thing because if you look at how, from the physics perspective first, I want to point out and just drive this point home. The synchronous case, the moth case, is a periodically forced oscillator. You know, like all these classic systems, Slinkies, Newton's cradles, ostriches running. The stretch activation case is an example of self-excited oscillations like you see in cardiac or neural dynamics. These little guys, this is my favorite example, right? There's a constant that you see outside of like used car lots, right? It's a constant jet of air going up, and yet it oscillates because there's a state-dependent coupling of the gravitational force as more of it folds over and then pushes up and then folds over. And so you get these oscillations from the state-dependent coupling of the forcing. So these are two pretty different ways of producing oscillations, a true limit cycle and then a forced orbit. So how insects switch back and forth. And so my postdoc mapped onto a family tree of insects. Here's a bunch of different insects, which ones were synchronous, that periodic drive, and asynchronous in red. And he said, how have these guys transitioned back and forth? And so what he did is he made a little Monte Carlo simulation where he basically tried to simulate the transition rates and find the transition rates for these different systems and then reconstruct the ancestral transitions across these in the evolutionary tree. And what he found is that, of course, the first insect, we already knew this, was synchronous. A periodic drove its wings. An example of one that diverged quickly there is the locust, the flying grasshoppers, right? And if you do that stretch pull experiment on them, they don't have that stretch activation. At least no one's been able to find it. And then what people had noticed, and if you look at the evolutionary biology literature, there's sort of four big groups: the hemipterans, which are like the true bugs, the bees, the beetles, and the flies that all fly with this self-excited oscillation. And the story has been that it requires so many specializations that it's evolved 4 times independently. But actually, according to the phylogenetic reconstruction, it actually evolved probably once. And all of these guys actually probably have the same common ancestor. And instead of evolving separately, what's happened is all the blue ones in the middle here have lost that ability and reverted back. And so if that's the case, it means that these guys, our moths and butterflies, actually have an ancestor that used to be stretch activated. And so what we were curious about that is, you should take this all with a grain of salt. It's hard to know what the actual pattern of evolution was, but it creates a really important prediction. If I look at the muscle of the moth that is normally periodically driven, does it have that stretch activation capacity still because its ancestors did? So we took that muscle out and we yoinked on it. And so here's the stretch step. And remember, it should have that stretch activation response. It has the capacity for self-excitation. And in fact, of course, I wouldn't be telling you this story if it didn't. It has that significant rise and fall. And actually, the time scale matches what you would expect an insect of this size to have as the time scale of it. But what's different is the magnitude of that force has been turned way, way down. It's like 1/3 of the neural force as opposed to 3 times what the neural force is. So they basically crank down the power of this self-excitation. But both mechanisms exist in the moth. So what that made us wonder is maybe what's driving these transitions is that you can have both kinds of oscillations coexisting in the same system. All right, so can we put those together into one physical model? So we take our self-excited model, we couple it with, and we scale the force appropriately to create the wing strokes. We couple it with a periodically driven force, and then we add these two together and have an interpolation factor that goes from fully self-excited to fully periodically driven, fully asynchronous to fully synchronous. And so now we in this model, I want to point out that the wing motion is not prescribed. The forcing is prescribed. But only the exogenous forcing for the synchronous case is prescribed. This is self-excited dynamics. So it's like having a feedback loop on velocity. So now we can create a parameter space that has 2 parameters, the strength of that drive from sort of stretch responsive to periodically driven, and then a ratio of time scales. This is the time scale of that force rise in the stretch activation to the resonant frequency of the system, the actual period of the system. And so we know that in this absolute case, it has to be synchronous. In this case, it has to be asynchronous. What happens in between? We see a very classic Arnold tongue. And so what an Arnold tongue here, right, is that in this region, everything's the frequency of oscillation is being totally driven by the nervous system. Everything collapses to the value of 1, which is the wingbeat frequency over the frequency of the drive in the system. So whatever you're driving is entraining the system to that frequency. But you hit a boundary that's quite sharp, actually, and you enter this red region where now all of a sudden the stretch activation has gotten strong enough and is at the right time scale relative to the mechanics that you get self-excited oscillations emerge. And the really interesting thing about this is if instead now I plot power as a color bar on here, what you'll see is that there's large regions of this space where it can produce oscillations, but basically the stretch activation and the periodic drive are fighting against each other because they're at wildly different time scales. And while you can get little oscillations, it basically destructively interferes and you don't get much aerodynamic power out of the system. But there's this bridge in the middle where you can have high-powered wing strokes that are asynchronous, synchronous, or even a strong mixture of the two, and you're still creating high-powered wing strokes. So this gave us the idea that maybe there's an evolutionary bridge in parameter space that allows you to switch from one mode to the other mode. So it would be cool if we could actually do that then. So the first thing we did is we built a dynamically scaled flapper that could instantiate this. We put a little torsional spring on it and oscillated that back and forth. And again, this flapper, we don't prescribe the kinematics. We prescribe the force and measure the kinematics. And then we can populate this now experimental data from that flapper. We can see this high-powered transition zone. So then, last 2 things, I'd like to say, well, it would be great then if I could take an insect and move it across this parameter space, right? So how can I do that? Well, I can take the moth muscle out of the animal, and I can couple it. So now I have an isolated moth muscle. I couple it to a computer model of our spring wing mechanics. So I put the muscle into a mechanical virtual reality environment where it's acting against a virtual wing. And the reason why I do that is because now I can also create a velocity feedback loop that mimics the effect of that stretch activation and applies an additional force in conjunction with the muscle as if I was turning up that KR knob and making it more asynchronous. And I can ask, can I get this model to self-excite And again, I probably wouldn't be showing you it if it didn't work. So we first block the synchronous activation, and we see that we can get self-excited oscillations. That basically has to be the case from the model, but it does create sort of stable oscillations there. So this is a force length trace that gives a positive loop, so it's producing net stable positive work. And then the second thing that we can do is we can put the synchronous drive back in at the normal wing stroke of the moths, and I can see if I can recapture that entrainment boundary. And so what I do now is let the muscle oscillate at its natural frequency, add in the stretch activation, and I tune the timescale of that stretch activation by, in the equation, in the virtual reality, tuning the timescale of the natural frequency. And so what should happen is if these two frequencies are far away from each other, then I should get a trace that has both frequencies excited, and my frequency spectrum at that sort of difference between the asynchronous and the synchronous frequency should have two peaks. If they exactly line up, then I should just get one peak where they cross. And if I can recapitulate that entrainment boundary, I should get entrainment where around that point, I'm always at a flat line. And so when I do that, or when Ethan does this, I really should say, I'm accelerating a little so we can finish up because I want to show you the robot at the end. He indeed finds those two peaks. In the middle, he finds the one peak. And then if we look at this, so that bounds this, and then if we fill this in, what we see is a nice entrainment region from about -5 hertz to about +5 hertz. In that region, the moth would be able to modulate its stretch activation and still produce high amplitude wing strokes from the periodic drive. In the last minute, I just want to say the very last thing we'd like to do is say, like any people who are collaborating with roboticists, can we build a robot that does these things, right? And so we took the Harvard RoboBee, which doesn't fly like a bee because it's periodically driven wing strokes, and we tried to make it fly like a bee. And so we put in that stretch activation, and we started the wing up, and it did that. It just sat there. And that's because there's a fixed point at 0, 0 that's unstable in a self-excited system. And so to ring up a limit cycle, you got to give it a kick. So we gave it a kick in our favorite way. We took our vortex gun, and we shot the wing with it. Boom. Oops, there, we hit it, and now it self-excites to a steady limit cycle. And we can show a transition between the two by taking that KR term. Now we periodically drive it, and then we transition it to a self-excited case. And so here it's oscillating at one frequency. You're going to get destructive interference because the time scales aren't matched here as we move through the intermediate range where it has both stretch activation and driven frequency. And then it's going to excite up to a new frequency. All right, and you might say, okay, great, Simon, that looks good. That's not a robot, that's a flapping wing. Can we get it to fly? We need two wings. Trouble with that is you put two wings together and there's nothing synchronizing the two of them. But remember, there's an elastic shell. And so if we put a little elastic element coupling the two wings together, now they flap in tandem. And we're able to get the first flight of a truly asynchronous oscillator driving these wings. So this is self-excited oscillations built through the state-dependent feedback built into these. Actually, there's no periodic drive of that. And you might say, why should we do that? Well, from the engineering perspective, there can be an advantage if I have something that blocks the wings, right? Like what happens if the wing hits a little trip line? But with the actual bee here, notice the wing just stopped when it hit that. That makes a lot of sense. You arrest the system, you stop all the velocity feedback, you're going to collapse to that fixed point at 0, 0 until you kick it back off again with the aerodynamic load. So you stabilize that fixed point with an external constraint force. And then when it removes, it excites back up. And so that means, unlike the periodic system where you just keep slapping into the obstacle, this can just stop. And the effect of this is that if we take a periodically driven, a synchronous flying robot, so this is where it's periodically driving the wings, and we try to fly it into clutter, it keeps bouncing around because of the large forces it produces on that. And this is the last video. If we use stretch activation instead, we can actually get it to fly up into this obstacle. And each wing stroke here, if we slow it down, is automatically adjusting to the forces that it's encountering from the surrounding environment. Okay, and so we just showed that a single unified biophysical model shows that these two forms of sort of coupling a self-excited oscillator and a periodically driven oscillator can actually go over an entrainment boundary, and that can describe the transitions that we're seeing in evolutionary flight. So we think these insects have jumped back and forth across this spectrum, and when they're close and have the right time scales, they can walk back, fly back and forth across that bridge in evolutionary parameter space, and then the groups that have specialized have changed those time scales so they get locked into one mode or the other. And with that, I'll thank everybody and thank you for the great questions.
right, we have, go ahead, Sharath.
I think I missed the last point about switching from one mode to another. You mean switching on evolutionary time scale? Or you mean every organism can, today I'm in the mood to fly
Evolutionary.
synchronous?
Yeah, we don't see any, I haven't found an insect yet that can do both forms itself. And I think that's because it doesn't have any ability to volitionally control the amount of stretch activation. So it's very hard to change that KR parameter and that timescale parameter in a single organism. But you can definitely evolve that. We know a lot of the molecular mechanisms, so not all of them, that underlie that, and so you could change those parameters over evolutionary time. So when I talked about that diversity of different flight structure, I think that's what's driving it. And I think what's driving frequency modulation here is the system most of these systems are super resonant, but they're still scaling with the resonant frequency. So the resonant frequency is a very important time scale that's driving a lot of the wingbeat frequency change in insects, but they're not locked to it. They are locked to not be below it, but they can be above it, and some of them trade off some of that power for more ability to control, and you get diversification in the wingbeat frequency there. What I really want to do is try and find an organism that's sitting on that bridge, and then look at its sister organisms and see if they've jumped back and forth. And that would be the true bugs, the hemipterans, because they've transitioned back and forth a lot in their evolutionary history. Yeah.
I wanted to ask something similar, like what's the evolutionary advantage of being super-resonant? So doesn't it cost Bumblebee more energy?
It does, but then it has the control ability, right? You can modulate, and like when you go back to that swing set, right? And if I ask you to modulate your wingbeat frequency by 30% from one wing stroke to the next, that's a really important affordance for control. It allows you to maneuver, do a lot of asymmetries between your wing. You can also pop the energy, you can make your energy on the two sides asymmetric. Everything I've talked about here is basically treated it as one muscle, but there's one muscle, downstroke muscle on this side, one on this side. They're usually going in tandem. Now I create a little bit of separation and I can create a wave of strain across that elastic exoskeleton that itself can do control. So we have some evidence that happens by left-right modulation of the two muscles, but we don't know all the control potentials, all the control effects of that, in part because this wing hinge is a very complicated joint. We're trying to model that now, actually. That's one of the projects.
You showed mostly or only insects with 2 wings, not 4, right?
Actually, almost all of those had 4 wings. The bumblebees and the moths have 4 wings, but the hind wings are effectively coupled to the 4 wings such that they act as a single wing. For most, at least most people assume that they can function well. So here, this is the forewing, back there is the hind wing. And so it basically creates one airfoil. Whether that's a totally valid assumption for all these cases, I don't think has been explored enough. The one place where they're really decoupled is, again, the dragonflies. You've seen that with the oscillating wings there, but that's a different actuation system too.
I have another question. I know other examples such as circadian rhythm, for instance, 24 hours, where cells themselves, chemical oscillator in cell, has period larger than 24 hours, which means it is driven the same
by
way.
the exogenous input, yeah.
Exactly, yeah. So is there some commonality of mechanisms or commonality of evolutionary goals or something?
Yeah, I think what this allows you to do is when those time scales are close enough, it gives you a bit of a push-pull between the exogenous forcing and the central time scale. The central time scale, as long as it's close enough, can get entrained to that external system, but it can also pull the system a little away from that if there's fluctuation. So it might help adapt to the changes in the driving forces. So what we haven't explored yet is what happens if we have like an asynchronous system and then we modulate the drive a little bit to it. It's usually pretty weak, but there is some ability to modulate that stretch activation by changing the other oscillator. So I think the fundamental frequency that arises is a pretty straightforward entrainment problem, and that's sort of what we've explored. The effects of like how you respond to perturbations when you have a self-excited oscillator coupled to a periodically driven oscillator, don't think that's been thoroughly explored yet, and that's one of the things we're really excited about for exactly those kinds of systems.
Well, so there. Oh,
Oh yeah, I did have one question. Maybe I should apologize for it, but I think you did say it was your favorite model. So those inflatable things at the car dealership,
Oh yeah.
how exactly do they work? You said
Yeah, it's interesting. So they have a jet of air. They have just a fan underneath, right? So there's a continuous jet of air going up, and then they have this kink in them, right, where they're falling over, right? And so basically, as the jet of air goes up, right, you get less and less stable because you have less and less of your mass up here that's in there, and so eventually you tilt over and you kink. And then the air can't get up there, and that kink propagates down as a wave, and then it blows back up once it gets strong enough. I haven't solved out the. There is somebody who's recently done a nice paper with the equations of that. I don't have it here. I can send it to you if you want afterward. But it is a classic self-excited system because it's a continuous forcing rather than a periodic forcing that then produces an oscillation.
All right, so there is wine and cheese downstairs, and we can continue conversing.